Tim, you could give like the brief elevator pitch just to remind our listeners of what it is and what you take the crucial points to be.
Well, again, I'll just say, and I'm going to kind of just channel what I learned from Shelley, maybe say something a little differently than he does that helped me. Everybody learns Newtonian mechanics at some point. It feels like they understand it. And usually with point particles, right? You treat even the Earth as a point or the sun as a point because it's easier to calculate, right? There are arguments why that's a pretty good approximation, but you're used to thinking of these particles moving around. And in Newtonian mechanics, the state of a system at a moment is given by the positions of these particles and their velocities or their momenta at that moment, right? And then you have Newton's equations, and that tells you the forces, and that tells you how the momenta change, and the momenta tell you how the particles move, and everything. You kind of see what's going on, right? So here's a thought. Get rid of the momenta. Just you have still particles, they still have positions. It's not it's a theory in which the particles' motions are now determined or guided by something else. And this something else is the wave function or the quantum state, this thing that's described by this wave function and Schrodinger's equation, and that's just common coin to every version of quantum theory. Everybody's got that. And you say, well, what's its role? What's it doing? Well, in this theory, it's guiding the particles. It's guiding the particle configurations. It's determining how they evolve. And then you say, oh, well, how does it do that? You've already got the wave function. You already got Schrodinger's equation that you can pick out of any book. You need an equation for that. And so there's an equation called the guidance equation. And it turns out, in the case of quantum mechanics, to be an unbelievably simple equation that, I don't know, Shelley says, I don't know, there are a dozen different ways you might arrive at it by heuristics. So you plug that in and it works. Gives you all the right predictions. I think you should be pretty impressed by that.
Okay.
Yeah, twofold impressed. Number one, because it's so nice that such a simple thing works, but that's with the background that almost the entire physics community had insisted that nothing remotely like that could possibly work. No hidden variables whatsoever could possibly explain quantum phenomena, quantum randomness, anything. Couldn't work. And now it turns out the most obvious thing in the world works. You're talking about a system of particles, so take it seriously. You've got particles, things with positions. Ask yourselves, how should they move? Let's make the obvious guess. You make the obvious educated guess. You got the theory, the wave function, particles moving in a certain way. Your natural thought would be at this point, okay, that theory can't possibly work. Because if something so simple worked, everybody would have accepted it. Nobody would have been talking about the impossibility of any such thing. Nobody would maybe talk about all this craziness, all this incomprehensible craziness. So, of course, that theory can't work. You analyze it and you find it works perfectly. Everything is explained. All the phenomena of non-relativistic quantum mechanics are explained in a completely comprehensible way.
And Tim, you said that the wave function determines the way that the particle configurations evolve. Mm-hmm. And I'm wondering, for our lay listeners, for me, how you visualize this happening. Is it something like, on a microscopic scale, a surfer being pushed by a water wave? Or
okay, yeah. So this is the thing that people say, right? People who don't like the theory say, oh, it's a cork being pushed around by a wave. The problem with that is that a cork is, for the purposes of that analogy, is a single point particle, and all it does is move somewhere or other in the ocean. what we're talking about being guided here is the configuration of all the particles. So unlike a point, that configuration already has a tremendous amount of structure, right? The configuration of, Avogadro's number, right? 10 to the 23rd particles. If I just give you that configuration, I can tell, is it a cat or is it a dog? Is it a sofa? Okay. If there's, to use one of Einstein's examples, if there's a keg of gunpowder, did it explode or not? Okay. If this keg of gunpowder has all those particles in it, and I give you just for a single instant its configuration, you can very easily tell whether it exploded or not, right? If it exploded, the configuration is the particles spread all over Kingdom Come. And if it didn't, the configuration is all the particles packed together in a keg. That's with no dynamical information, with nothing going through time, with no considerations about counterfactuals, with no considerations about anything. Just the configuration of many particles has already a very important structure that makes this thing interpretable. So if you think that entire configuration you're thinking of as just a cork and all it's doing is bobbing, then you're going to be very puzzled. You're going to say, well, wait, how does the cork have to bob in order for me to break my leg? How does the cork have to bob in order for a needle on a meter to go this way rather than that way, or to a spot to form on this part of the screen rather than that part of the screen? You'll be very puzzled about that. But if you see, no, it's not a cork. It's a configuration of as many particles as you like. And that contains, those are the local beables, and that contains a tremendous amount of information about what's going on, just even at an instant. That's why it's entirely misleading to think of it as a point. And that's why, I mentioned to you the many worlds people who say, oh, this Deutsch nonsense about how Bohm is just many worlds in a state of denial. Why? Well, you've got a wave function. It never collapses. So you've got all these branches. And then Deutsch says, look, there are these many worlds. And then you want to say, no, because there aren't any worlds that I can recognize because you don't have any local beables. When I add the local beables, I add a whole lot of them. I don't add a single point. And its purpose is not to indicate a branch of the wave function, which is what they say, right? Its point is to be the world we're familiar with cats and dogs and chairs and tables and people and meters, right? And laboratories and people doing experiments. All of that's in the particle configuration, or it can be recognized in the particle configuration. So that's why this picture of a cork bobbing along will really take you the wrong direction. It's the entire configuration changing, right? That is what the wave function is coordinating or choreographing.
But let me say something else about your question. You're really asking, okay, how can we understand why the particles should move this particular way? And often people want to have, oh, it's like this, oh, it's like that, oh, it's just like, Bohm talked about particles being like a little radio receiving information from the wave function or whatever. These things, they may help some people, but they are entirely misleading. You have to ask yourself, how does a fundamental physical theory work? If you say, oh, the way it works is I have to appeal to a deeper theory to explain what's going on, then it wasn't the fundamental theory. If it's a fundamental theory, your questions have to stop somewhere. If you have compelling mathematics describing how the local beables evolve, and then you're going to say, oh, but that's not good enough. Even though it's compelling, it's simple. But why should it be that way? And you want to say, oh, I have to understand that in terms of something more familiar. Why should you expect that? This is the fundamental theory. What more do you want than having a theory involving simple structures evolving according to simple laws of motion? Why should you have to derive those laws of motion from something else?
Right. Feynman made this point in a very nice interview. Maybe you've seen it, where somebody's asking, well, can you really explain, for example, why there's an electrical attraction between a positively charged and a negatively charged particle? Can you explain that? And he said, well, I could kind of try to give you a model in terms of rubber bands or something, which might make you feel better. But he said, but that's a cheat, because the way rubber bands work depends upon electromagnetic theory. I mean, you've got the whole thing upside down. I'm appealing to the fundamental electromagnetic theory to explain rubber bands, so I better not be putting rubber bands into my understanding of the fundamental electromagnetic theory. I mean, explanation has to come to an end somewhere. My dissertation advisor, Clark Gleamore, in his book says more or less the same thing. He says, look, sometimes when something happens, there's like a Rube Goldberg device, right? You know, why does the kettle get taken off the stove? Well, there's a man walking along and he slips on a banana peel and he falls and he pulls this and this happens and that happens. And he says, but that can't go on forever. You can't say, well, but why is the banana peel slippery? Well, now you put another Rube Goldberg device to do that, and then yet another one to explain all the mechanisms of that. That's just a mug's game, right? That's just silly. Where do you end in your explanation? You end somewhere simple. You end somewhere where it feels like this would be a good place to give up asking for further explanations, right? And that's just simplicity and clearness and things like that. So, you know, you shouldn't, what more could you expect? If you expect more than that, and certainly if you expect an understanding in terms of your everyday experience, that's just silly. Why should your everyday experience be a good guide to how quantum states make configurations, you know, direct configurations?
Okay, you've given me enough ammunition for quite a few questions, and let's see where I should even start. Maybe I should start with the quark metaphor, and I think that the quark metaphor probably arises from popular physics. Well, maybe I have no idea where it arises actually, but I know where it arises for people like me is in popular physics books that describe Bohmian mechanics, usually in the context of something like the twin slit experiment. You get an image of a wave guiding an electron, like it's a surfer on a wave. And I'm wondering, yes.
Yes, but I make a comment about that.
Please.
A single particle system, which is what you're looking at there, a single particle, you have this very, very, very special situation that the configuration of a single particle, the configuration space of a single particle is physical space. That is, you specify what we would call the configuration of a single particle simply by telling me where it is. So the wave function, which is defined on configuration space, for a single particle and only for a single particle, can be pictured as a field on physical space, like a water wave. But once you get up to two particles, nope. Because the configuration space for two particles is 6-dimensional, and the configuration space for three particles is 9-dimensional. And the configuration space for 6 times 10 to the 23rd particles is a hell of a lot bigger than physical space. So it's okay to think of the two-slit experiment for a single particle in that way, as long as you're aware that it is a very, 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 very special situation, which would be extremely misleading if you thought it generalized beyond a single particle in that way. That once you get to more than one particle, the wave function is not defined on physical space. You can't picture it as something on physical space. It doesn't have values in physical space, and so on. Does that help? I mean,
no, that helps quickly, because obviously, I mean, we can't envision 4-dimensional object. I mean, it's well documented psychologically. I think that people can't envision a hypersphere or a hypercube or something like that. So clearly, we're not going to be able to come up with a good visual metaphor for something that's 6-dimensional, or God forbid, much bigger than that. So no, that's
something what Tim just said. If you want to understand the nature of the wave function, you better be thinking about more than a wave function for a single particle. because you're going to get entirely the wrong idea if that's what you're focused on. The essential innovation that is the wave function arises when you consider the wave function for more than one part.
And then, Shelley, you said some very interesting things about Bohmian mechanics as a fundamental theory that I want to get back to in one moment, because I wanted to first finish up Tim's handling of the criticism leveled by David Deutsch and the Oxford people in defense of many worlds, where, if I'm correct in recalling what you just said, they sort of labeled Bohmian mechanics as many worlds plus a particle configuration. And did you also say that Bell had already, you might have said this in an email to me, that Bell had already addressed this earlier on?
I'm not sure.
Just what?
Bell didn't spend a lot of time on many worlds. The only many worlds theory he could understand was not the standard one with splitting. He came up with what's called Bell's many worlds, where you always have a single particle configuration, but it jumps around at random. At every moment, it kind of jumps around in accordance with the square of the wave function. That's not the one that the Everettians have in mind. I don't know if Bell ever talked about the kind of splitting and stuff like that happens.
Well, Bell was well aware of it, but that was all too vague. In trying to get to the heart of what he took to be Everett's proposal, he first demanded a clear ontology for the worlds. And that was a particle ontology. Anything, because Bell demanded a clear ontology. And then he somehow realized that insofar as the theory explains anything, he doesn't need all the worlds. One would be sufficient. So he threw out all the rest, which makes it a very eccentric version of Everett. He calls it Everett with a question mark. And then in exploring the details of his version of Everett, which he thought was ridiculous, he points out how ridiculous it is. It leads you to a complete reduction ad absurdum. If you believe his theory, you can't believe anything.
Right.
Yes, he points out.
This not many people are going to follow it, but I just have to say it because it may be lost. I don't know if it's printed anywhere. Bell gave a talk at the PSA meetings back in the 80s. And in that talk, he talked a little bit about part of what was going on in many worlds, which was decoherence. I'm sure you've had people bring up decoherence. Okay. So kind of a picture in your head is if you had a big matrix that's representing the wave function, if it decoheres, then the only entries are down the diagonal and all the off-diagonal elements have somehow gone to zero. All right. So this is just a kind of picture in your head of what you're looking for decoherence. And Bell made a wonderful comment, because this was when so-called environmental decoherence was becoming very, very fashionable. And he said, well, it's true that if you pick any of those off-diagonal elements and wait long enough, it will get as small as you like. But he said, but it's also true that no matter how long you wait, there'll be some off-diagonal element that it is as big as you don't like. So he thought that all of these arguments were really, again, just logically flawed, who were people who were looking at decoherence as somehow magically solving these problems. But it was a wonderful, this is just Bell again, kind of making this wonderful comment.